So we are going to talk about chapter 16, electromagnetic waves. So this is the kind of a conceptual diagram. So you will see that electric field and magnetic field is a kind of a AC type of a modulation, but note that it is given by is function of both space and time. Magnetic field also function of both space and time. So it is, you'll see that it is I k. Wait, this is the x directions. So assume that this is the x direction. So it's going to be x minus omega t, or cosine kx minus omega t. In the previous chapters, we were dealing with the AC, so that the current and the voltage is changed with the time, like a cosine omega t or sine omega t. But this kind of a modulation is expanded into both space and time. That's the wave. And then we are going to solve the very fundamental aspect of the electromagnetic waves. So if you look at the key equations, there is a so-called displacement current that is due to the electromagnetic flux change. So if there is an electric field is changing, that is bring the current, and this current is once again is going to generate a magnetic field. So magnetic field and electric field is talking to each other. We have seen that before. This is the Faraday's law. There's a magnetic field and a magnetic field here, and the electric field is changing, vice versa. So we are looking at the same thing here. So in order to understand the nature of electromagnetic wave, we need to understand the Gauss law, that is relating electric field with the charge. And then Gauss law to magnetism, we have the same form over integral, but it goes to zero because there is no magnetic charge. There's an electric charge. Or magnetic charge is magnetic monopole. And then this is relating the magnetic field's time dependence. Time-dependent magnetic field is related with the electric field. And then here comes the modified Ampere's law, and by addition of this, we call it Ampere-Maxwell's law. Here, if there is even though there is no current, this time is zero, let's assume, then you'll see that and you'll see that it is exactly symmetric form of the Faraday's law. So time-dependent magnetic flux, or B, is inducing electric field. Similarly, in the Ampere-Maxwell's law, you will find out time-dependent electric field will generate magnetic field. And then by arranging these equations, you end up with the wave equations for plane wave, like this. So you have seen that this kind of a wave in the physics 161. And then in the wave, you have a lambda and lambda or k in the space domain. And there is a f or omega in time domain. Modulation in space is given by these wavelengths. And the time domain, your modulation is determined by this frequency. And if it is a wave, you get lambda times f, which is the length over time is velocity of that wave. In the case of an electromagnetic wave, that velocity is light velocity, c. Okay, that is the important one. So electromagnetic wave is a kind of wave, but it is propagating with the speed of the light. Okay. And then in the plane electromagnetic wave, the electric field and magnetic field has a fixed ratio, which is given by, once again, c. So in the electromagnetic wave is more or less defined by the light velocity, c, in a way. And then there is a Poynting vector, which is defined by the E cross B, and then it is the energy flux. And then this energy flux is related with the intensity, which is given by this E square, and then we note that this is related with the B square, or you can have both E0, B0, okay? And it looks like a kind of a IB, okay? And then radiation pressure, if you have a intensity, light is impinging upon certain area with a certain intensity, and then the radiation, the light will give you a certain pressure, and there is two cases. It is perfect absorbing, and it is given by I over C, and it is perfect reflector is 2I over C. So anyway, this is the formula, and then you will see that the formula is not that much, and then we can memorize the formula more or less easily, and then we can apply the formula to the problems. So suppose the parallel plate capacitor shown below is accumulating charge at the rate of this one. This is a QT. And what is the induced magnetic field at the distance of 10 centimeter from the capacitor, so that this is the distance. And this is directly related with Ampere Maxwell's law. If you go back, this case. So in the capacitor, you will see that because it is there's a gap, there is no current source, but instead we have this time-varying electric field. And this serves as a kind of a current. And then if you have a current, you get the magnetic field. Okay, this is called so-called displacement current. Note that it is proportional to d phi E over dt. So now let's try to find out what is changing. So we have a charge accumulation rate, dq over dt is given And distance from the capacitor center is 10 centimeter, and then it is given 0.1 meter, and then etc. etc. Okay, so now it's time to think a little bit more about these situations. So we are looking at the distance about this much, which is the 10.1 meter. And what is happening here is that the QT is time varying. And then as a result, electric field will be also time varying. And this flux across a certain loop will also change with the time. So that's the main thing. And then we are going to have an Amperian loop with the R equal to 0.1 meter. And then apply the Ampere's law for this loop. And then you will have this d phi E over dt is the main source of the current in this region. Note that between the capacitor, there is no current, but only the time-varying electric field. And then if the time-varying electric field, then we get the time-varying electric flux, and then you get the d phi over dt, and then this will give you magnetic field. Okay, that's the logic. So we have, once again, Ampere-Maxwell's law. We have this relationship. We have to get an Amperian loop over Amperian loop with radius r. And this is our radius. And then we are going to have I enclosed. If you look at it, there is no current, so that this should be 0. Okay? And then the only term is given by mu 0, epsilon 0, d phi E over dt. And then let's try to think about a parallel capacitor, and then we have this displacement current, okay? And then let's try to find out. So for the circular path, pi r, and then we get this displacement current. And this displacement current is given by this one. And then we need to find out displacement current is actually this. Okay, dq dt is given. And this will be our current. Okay, and then we just plug in dq dt. T is our displacement current, and then we can get the magnetic field. Okay. And while outdoors on a sunny day, a student holds a large convex lens of a radius of 5.2 centimeters over a sheet of paper to produce a bright spot on a paper that is 1.4 centimeter in radius. Okay, so we have a convex lens. So let me see. So we have a light lens. So radius is certain with this focusing spot. And the distance is actually 5.2 centimeters. And then this diameter, radius is given by 1.4 centimeters. Okay. And by what vector is the electric field in the bright spot of the light related to electric field of a sunlight leaving the side of the lens facing the paper? So that we are going to look at the utilize the intensity formula because it is given by a certain area, so we have to think about intensity rather than power. And then intensity is nothing but power over area. And if you look at it, it is proportional to electric field squared. Okay. And then we have to think about energy conservation. P in should be P out. And the PI is, power is intensity times area. Note that intensity is power over area. Okay. So the power is intensity times area. Okay. So what it means is the P in intensity of the sunlight and the area of a lens should be same as intensity of a spot and area of a spot. Okay, so we have this relationship, and then we need to calculate one by one. The area of the lens is this one. Spot area is given by this one. And then I spot over I sun is given by I lens over I area spot. And then we get intensity ratio over this number. And once again, note that intensity would be electric field square. The question is how the electric field is going to be scaled. So E spot over E sun is going to be square root of this one. And then you get this number. So this is the scaling factor. So initially it was the E spot. In other words, by a focusing lens, your electric field is increased by this much in comparison to the electric field of the sunlight. Okay. So focusing will give you increase the electric field. And another problem here is the 190 watt light bulb emits 5% of its energy as electromagnetic radiations. And so what is the magnitude of average pointing vector 10 meter from the bulb? So once again, we have a light bulb. And it is radiating. It's a 10 meter. And then what we have to think about is the 10 meter long, we have a certain uh, uh, sphere. And then we have a power is already there. And then we have a S pointing vector is given by P over area. If you note that it is same as intensity. So intensity and the pointing vector are directly related, okay? There's some scale factor, but basically is watt per meter square. This is a power over area and radiated power and area over which the radiation spreads. So we have to determine what is going to be the radiation power. So 190 watt bulb emits 5% of its energy as electromagnetic radiation. So that out of a 190 watt, we have to multiply 5%, which is 0.05. This is our radiation power. And then we have to think about what is the area. Note that it is emitting all around, so that the area is 4 pi r square, the sphere. So here is the light bulb, and then we have a And then what we can do is that we know the radiation power is, and we know the area is, and then we can find out the average Poynting vector. And that is the numerical value you can get. And next problem, as an AM radio transmitter broadcast power, this is the radiation power, uniformly in all directions. Okay, assuming all the radio waves that strike the ground are completely observed, and that there is no absorption by the atmosphere or other object, what is the intensity of a 30 kilometer away? So it is related to the previous problem. So intensity of electromagnetic radiation is given by power per, the intensity is defined by the power divided by the area. And then area is over which the power spreads. Okay, so this is the case. So area of a spherical wavefront is 4 pi r square, as we have seen before, because it's uniformly spread in all directions. Okay. And then we need to calculate intensity is given by power over area. Power is given by this one, area is given by this one, and then intensity is given in this number. Okay. An industrial laser is used to burn a hole through a piece of metal. The RMS value of the electric field is given by this volt per meter. And what is the RMS value of the magnetic field? So electric field values is given, and then find out the magnetic field magnitude. So we have to go back to a kind of a formula. So we note that if it's traveling in a vacuum, and then this is electric field magnitude, and the magnetic field magnitude is related by the E equal to C times B. Okay, same as for the Riemann scale value. Okay, so that what we have to do is that go back to this very simple formula, and then plug in ERMS and the C here, and then you can get Tesla. Note that you should have a volt per meter, meter per second, okay? And then you get the Tesla. So if you look at it, electric field is quite high, 1 times 10 to the 6 is 1 million volt per meter, but magnetic field is relatively small. So in fact, 1 Tesla is quite a significant magnitude. And then by this relationship, E equal to CB, most of the energy is actually delivered by the electric field. Magnetic field intensity, magnetic field magnitude is relatively small. Very strong electric field correspond to magnetic field of only a few millitesla. That's the things you need to understand, okay? And now a thin tungsten filament with a length of 4.1 meter radiate power in the form of electromagnetic waves, perfectly absorbing surface in the form of a hollow cylinder with a radius of 6 centimeters and the length of 4.1 meter is placed concentrically with the filament. Calculate the radiation pressure acting on the cylinder inner circular surface. So what is happening here is that the filament is radiating, and then there is a cylinder, and that is absorbing this electromagnetic wave inside inside the surface. That's the situations. Okay, so let's try to find out how it goes. So radiation pressure for an absorbing surface is given by I over C. If it is perfectly flattening, there is a factor of 2. Okay. But it is perfectly observing such that the radiation pressure is exerted in the form of I over C. Okay. And we need to calculate I, and then we can get the radiation pressure right away. But I is given by radiation power per unit area is given by this one, by unit area. But note that we are in a cylinder. So that's the thing. Previous case, A was the sphere, but now we are in a cylinder. So cylinder radius and the cylinder length is given. And then we get the area is 2 pi RL. That's the thing. So let's try to find out the radius is given, length is given. You can get the area in the meter square. Okay. And then you get the area here, and the power is already given here. And you get the intensity, and this intensity will be used to calculate the radiation pressure. Okay, that's the logic. So all the formula is rather simple. Okay, so just try to connect all the formulas logically and try to get the right numerical value. The next problem is electric field of electromagnetic wave is given expression. So the electric field is given, this is the amplitude, and this is holding is actually omega t, omega, okay? Where all quantities are given in SI unit. What is the frequency of the wave? Frequency. Remember that 2 pi f is omega. So electric field of a plane electromagnetic is usually is given by is modulating in the space, modulating in the time. Okay. So if it is modulating only in the time at a certain fixed position, and then it's given by omega. And then omega is given by 2 pi f. And then from this given electric field, we need to find out omega t, the whole thing. In front of t is omega. In front of t, whatever it is, in front of t is omega. Okay. And then once you find out omega, you get f. Okay, this is the numerical value. Once again, it is very simple. You need to identify what parameters are given. In this case, the frequency is given. The angular frequency, omega is given, and then the question is, what is the f frequency? And then it is very simple formula. What capacitance is needed in series with an inductor to form a circuit that radiates a wavelength of 300 meters? So we have a LC circuit. Okay. LC circuit, and then we need to find out the C, the capacitance. Note that this C is not the speed of light. This C, small c, is the speed of light. And we want to find out C, capital C, okay? And then try to find out what it is. So the wavelength is given, lambda is given, So this is very similar to what we have seen in the physics 161. If there's a wave, lambda times f should be the velocity. But in the case of electromagnetic wave, this velocity becomes c, speed of light. So that c is f lambda. Okay. And then from this, lambda is given so that we can find out the frequency. And the resonant frequency of a LC circuit is given. Once again, it is related with previous chapter, chapter 14, chapter 15. And then this resonance circuit is given by this formula. And then that is actually, LSC works as a kind of a oscillator. Remember that LC circuit works as an oscillator. That means the electric field energy and magnetic field energy is oscillating back and forth, and that is a starting point of electromagnetic wave. So in that case, we have a resonance frequency given by this formula. So L, inductance, and the capacitance. So inductance is given, and this is what we need to find out. And then if you take the squared on both sides, and then f squared is given by this one, and then you get this formula. Okay. So first thing is that you need to find the frequency from the this relationship that is relating your wavelengths with your frequency. And then second thing is that this frequency is related with the resonance frequency of LC circuit. Okay, here. And then we can find out unknown capacitance. So once again, it is very simple formula. You use the two formulas, but you have to connect them logically. So actually, LC circuit acts as a kind of a radio transmitter receiver oscillator and to emit the radiation of a wavelength of 300 meter, which is about 1 megahertz. The inductance and the capacitance must satisfy the resonance condition. That's the basis of this problem. Now let's look at another problem. What is the maximum electric field strength in an electromagnetic wave that has a maximum magnetic field strength over this one? Okay, so we need to find out electric field for the given magnetic field and the speed of light. Now you should be able to find out very easily. And E is CV. Okay. It's a very simple problem. It's very, very simple. And finally, of infinite current sheet lying in the y-z plane carries a sinusoidal current that has maximum density of 4.62 ampere meter. Find the maximum value of a radiated magnetic field. That's the things. So we have to think about it. What is happening here is that we have a YZ plane. So let's say this is the Y. I think this may be wrong. This is the Y minus Y plus G. And then it carries the sinusoidal current. And it is, note that it is the current density, okay? So it's a surface current density, kappa. And you need to find out magnetic field due to this one. And if you look at it, you have a surface charge density, you have an electric field. And similarly, if you have a surface current density, then you get B in both sides. Okay. And then it is very similar to each other. This is surface charge density, and this is surface current. And then surface current and the magnetic field is related with this simple formula. And then you just plug in the right value, U0 and K value here, okay? And then you can get the magnetic field. So once again, it is very simple formula, and then substitute right numbers. Okay, that's it. So that in terms of physics, electromagnetic wave might be quite difficult to understand. But this exams is very simple. It's a simple and direct utilization of a formula, so that if you work hard, you will get high marks for sure. Okay. Okay, that's it. And then we'll stop.